After talking about the sun, our next topic of study is going to be the planets. Solar system, that's the name of the class. And so, first planet we're going to talk about is the planet Mercury. So your book puts Mercury, Venus, and Mars all in one chapter, and kind of talks about them parallel. I'm going to talk about more sequentially. Mercury is always very close to the sun, and so it has a very elliptical orbit. And so as Mercury goes around the sun, because it's so elliptical, sometimes, the greatest elongation, the farthest it gets from the sun, is 18 degrees, and sometimes it's up to 28 degrees, almost double as far away. And so that means that as it goes around, if you try to look at Mercury, if you happen to look at it when it's close to the sun, it's going to be very hard to see, whereas if you look at it when it's far from the sun, it's going to be easier to see. 28 degrees is almost 30 degrees. 30 degrees difference is about the distance the sun travels, or the sky moves in a couple hours. So that means the sun would set and then Mercury would set a bit later. That means you'd actually see it in twilight. Whereas if it's only 18 degrees away, it'll be setting towards the end of twilight. The other thing that happens is the ecliptic, the path the sun takes along the sky, is sometimes at a shallow angle relative to the horizon, sometimes steep. That also makes a difference as to whether you get a good view of Mercury or not. The difference in perihelion and aphelion is really quite striking. That makes Mercury one of the most elliptical orbits of the planets. It takes about 88 days to go around the sun. Okay, so as I said, the elongation can either be a favorable elongation, in which case it's a long ways away from the sun and at a steep angle, or it can be an unfavorable elongation, which means it's not very far from the sun and it's at a shallow angle relative to the horizon. Something like this, where it's an unfavorable elongation, might set just as the sky is starting to get dark enough to even see it. So you might not even see the planet because it'd be setting during bright twilight. Whereas in this case, the planet would be visible for a short time after twilight. And so that would be the time you want to see it. So this is the best time to see it. Now, the problem is, as Mercury goes around the sun, its orbital period is 88 days, but the synodic period is about 115 days, or 116 days. Now, the problem is that means that that's almost two sidereal periods in there, and so that means that really, when you see Mercury, you can think of it as Earth goes around the sun, Mercury goes around the sun. So you've got Earth and the sun here. Mercury going all the way around. That's going to be 3 months here. And then in 3 months, Earth is up here. And so that means that you get an orientation like that. And then 3 months later, Earth's over here. Now Mercury is lined with the sun. You don't see it. And then 3 months later here. Now that means that really the best time to see Mercury is about every 2 Mercury orbits. Now that turns out to be very important. So every 2 Mercury orbits, you see Mercury well. Okay. From Earth, Mercury looks pitiful. It's always really close to the sun. Mercury's only slightly bigger than our moon, so it's a long ways away, and you normally see it low in the sky through a lot of atmosphere because you can only see it during twilight. So the sky conditions aren't great. And so these are views from Earth, and so you barely see anything on there. There's a hint of bright and dark regions on there, so it's very difficult to see details. So for the longest time, astronomers did not know anything about Mercury other than where it was relative to the sun. And they could tell it was a rocky world, and it seemed to have no atmosphere, and that's about as far as they could tell. There were arguments about the nature of the surface. It's always real close to the sun, so they figured it's going to be really hot. They didn't even know how fast it rotated because it's very difficult to look at that and actually see markings and see them moving. Mercury does pass between the Earth and the sun. And so these are pictures that I took of a transit of Mercury in 2006. Now, trying to determine the rotation rate of Mercury. As I said, the best observations of Mercury happen every 2 Mercury orbits. Now, Giovanni Schiaparelli, a famous Italian astronomer in the late 19th century, was looking at Mercury using the best telescopes that were available in Europe, and he looked at Mercury when it was at greatest elongation, favorable elongations, because the favorable elongations occur every 2 orbital periods. Yeah, so he looked at that and looked at it and said, well, it looks to him like the same markings were there. That was very, very difficult to see bright and dark markings, but he thought he saw some, and he thought every time he looked at it, he saw the same side lit up. Now, the assumption was that if you always see the same side lit up, then that side must always be facing the sun. Now, we know that the moon, as it orbits Earth, is tidally locked to always face one side towards Earth. And so astronomers believed that Mercury was the same way, one side always facing the sun. So that means that side would never see nighttime. It'd get hot, 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 hot because you're facing the sun, you're really close to the sun, and therefore there was even some speculation that it might eventually heat up to the point that it melts. The other side would be permanently frozen because even though it's really close to the sun, it's facing away from the sun never shines on it, and it would be very, very cold. So this was the idea that people had about Mercury, and in fact, when I started school, in elementary school, that's what one of the books said Mercury did. Well, that's what the book said Mercury did. But at Arecibo Radio Observatory, they also have the world's most powerful radar transmitter. And so they could fire a radar beam that would then bounce off that reflector and go across the solar system and bounce off of Mercury and come back. And so as Mercury is rotating, then what happens is as Mercury rotates, one side of Mercury is coming towards us, so that side is going to be blue shifted. The other side is going away from us, so that'll be red shifted. By measuring that difference, then we can figure out the rotation rate of Mercury. So this was mainly done just to confirm what everybody had already was pretty sure of, that Mercury rotates synchronously once every 88 days. Well, what they found was it does not do that. Instead of rotating synchronously, because this is what everybody thought, was that Mercury rotated synchronously so that one side's always facing the sun, is evidenced by those little red dots in that diagram. Okay. What they actually found was that Mercury does rotate about once every 58.6 days. So that's about once every 59 days. Well, that's 2/3 of the orbital period. So that means that it's 3-2 spin-orbit coupling. That means as it goes around, then it spins exactly 1.5 times for every orbit. And so, again, these diagrams, by the way, are on page 301 of your textbook. So this orientation here was what they realized. Now, what that means, though, is this is an elliptical orbit. Elliptical orbits speed up and slow down. It turns out you're closest to the sun, that's where the orbit's going fastest, that's where gravity has locked it. So as it's swinging by close to the sun, it keeps one side towards the sun as it's swinging by at perihelion. But in order for it to rotate at the right speed to do that there, it's going too slow up here, and so it gradually rotates. Or sorry, it's going too fast over far away, and so it gradually rotates. And so the next time by, it points the other side of the sun. So every time it goes by, it flips. But that means after it goes around twice, it has rotated exactly 3 times, and so the same side is facing the sun. So Schiaparelli was actually right. He saw Mercury every 2 Mercury orbits, and he really was seeing the same side lit up, because the same side was facing the sun every 2 Mercury orbits. Given the the equipment of his day and the fact that this was done all visually, this was unbelievably spectacular observations on his part. His interpretation was wrong, and all astronomers since then were wrong up until the Arecibo measurements that were made. Actually, they were made about the time just before I started elementary school, but the elementary school book that I had still had the wrong thing about Mercury being synchronous rotating.